In Module 4, Lesson 32, we're going to look at multi-step problems in the real world. So our opening exercise, which is normally reviewing what we did in the lesson before, we see that Chin is buying beverages for a party, which are individually packaged and come in packs of 8. P is going to be the number of packages Chin buys, and T will be the total number of beverages. The equation T equals 8P can be used to calculate the total number of beverages when the number of packages is known. And we were to determine the independent and dependent variable in this scenario, make a table using whole number values of P which are less than 6. So our table was started for us already. Our independent variable is the number of packages. Our dependent variable, again, which is dependent on how many packages we buy, is the total number of beverages. So if we buy 0 packages, 8 times P, 8 times 0 is 0. If we buy 1 package, 8 times 1 is 8. For 2 packages, 8 times 2 is 16. For 3 packages, 8 times 3 is 24. For 4 packages, 8 times 4 is 32. And for 5 packages, 8 times 5 is 40 beverages. Now in example 1, we're going to take that information and we're going to graph it. So in this graph, we need to graph our independent variable on the x-axis. So this will be our number of packages. And our dependent variable will be on the y-axis. And this is the total number of beverages. Then we need to create a scale on each of the axes that will allow us to fit all of the points on this graph, keeping in mind that we start at 0 for both axes. Now we were buying small numbers of packages, 1 through 5. So on the x-axis, we'll put 1 through 5. And we're numbering the lines, not the spaces. So we'll go up to 6 here. And then on our y-axis, following the same pattern that we had in our table, we're going to go up by 8s. So we'll have 8, 16, 24, 32, 40, and then on the top would be 48. So we take each of our variables. The independent, remember, is our x-axis, and the dependent variables are y-axis. So when there are 0 packages, there are 0 beverages. We put a point on 0, 0. And when there is 1 package, there are 8 beverages. 2 packages are 16. 3 are 24, and so on. And then just to show the relationship more clearly, we'll draw a line connecting those points. And the purpose of the line graph then will show us that we can tell any place along the continuum how many beverages there will be depending on the number of packages that we have. So in example 2, we're given the graph, and they're asking us to determine which variable is the independent variable and which is the dependent variable. Then state the relationship between the quantities that are represented by the variables. So 0, 0, the number of hours and the number of miles, doesn't really tell us very much. But at 1 hour, it is 50 miles. And at 2 hours, it's 100 miles. So the number of hours must be our independent variable. And our dependent variable would then be the number of miles. The relationship between the two, the number of miles, would equal 50 times the number of hours. In the exercises then, we'll be working on creating the table and then the graph for each of the relationships. So in number 1, each week Quentin earns $30, and if he saves this money, we would create a graph that shows the total amount of money Quentin has saved from week 1 through week 8. We'll write an equation that represents the relationship between the number of weeks that Quentin has saved his money, W, and the total amount of money he has saved, which is S. And then we'll name the independent and dependent variable and write a sentence that shows the relationship. So in our table, our independent variable would clearly be the number of weeks. And that'll be represented by W. The dependent variable then would be the total amount of money saved, which will be represented by S. And S is equal to 30 times the number of weeks. So we see in our table the number of weeks times 30, which is $30 per week, will give us our dependent variable, which is the total money saved. Now, in our graph, we're going to graph these values. Our x-axis is going to be the independent variable, which is the number of weeks, and our y-axis will be the total money saved, which is our dependent variable. And so what you might have noticed is that our graph doesn't have enough lines to take all of the points in our table. But with a line graph, once you've established enough points to make the line, it is assumed that it would continue in that same pattern. So we don't have to be able to graph every single point in the table, just enough to show the pattern. We need to label both of our axes. It's a very important part, so we'll take a moment to do that. In exercise 2, Zoe is collecting books to donate. She started with 3 and collects 2 more each week. She's using the equation B is equal to 2W plus 3, where B is the total number of books collected and W is the number of weeks she has been collecting. We need to name the independent and dependent variables and then create a graph to represent how many books Zoe has collected when W is 5 or less. So first we'll make the statement. The number of weeks is the independent variable. And the number of books collected is the dependent variable. In our table, We'll put the number of weeks, our independent variable, first, and the number of books collected as the dependent variable. And then we're going to do data for weeks 1 through 5, or 0 through 5. Number of books collected, 0 times 2 is 0, plus 3 is 3. 1 times 2 plus 3 is 5. 2 times 2 plus 3 is 7. 2 times 3 plus 3 is 9. 2 times 4 plus 3 is 11. And 2 times 5 plus 3 is 13. So we label our graph, and then we need to put our scales on the x and y axis. The x-axis showing the number of weeks, we're counting by ones. The y-axis showing the number of books collected, we're going to count by twos, even though the numbers don't go exactly on a line. It is the best way to represent well enough for us to tell what the numbers are. So you can see when we graph our points, at 0 there were 3 books collected. At 1 week we had 5. At 2 weeks we had 7. At 3 we had 9. At 4 we have 11. And then it would continue off of the graph. And finally, in exercise 3, Eliana plans to visit the fair. She must pay $5 to enter the fairgrounds, an additional $3 per ride. We're going to write the equation to show the relationship between R, which is the number of rides, and T, the total cost. Then, of course, state which variable is dependent and which is independent. So the independent variable is the number of rides. And the dependent variable is the total cost. Our expression then would be T, the total cost, is equal to 3 times R, 3 times the number of rides, plus 5, the cost to get in to the fair. We'll create a table where our independent variable, which is the number of rides, is listed on the left, and the total cost, which is our dependent variable, in dollars, is on the right. And we will start with 0 and go up through 5 rides. Cost in dollars, if you ride no rides, it's still $5 to get into the fair. 3 times 1 plus 5 is $8 if you ride 1 ride. 3 times 2 is 6 plus 5 is 11 for 2 rides. For 3 rides, 3 times 3 is 9 plus 5 is 14. For 4 rides, 3 times 4 is 12 plus 5 is 17. And for 5 rides, 3 times 5 is 15 plus 5 is 20. So then we'll set up our graph, label it, put in the scale for our x and y axis, and plot our points to show the relationship. And so we see our table graphed, and you'll notice that in my choice of scale for the y-axis, counting by twos, I was only able to fit 3 of the points on there. But remember, in a linear relationship like this, it shows the trend, and we know that it would continue in a straight line the same way. So you don't have to fit every single point in your table on your graph.